Okay, hi everyone. This is the third time we are hosting the Quantum AI monthly series. It's a joint effort between Bibliotheca Alexandrina and iQafé. Yeah, this is like our third month. It's not the third anniversary, but the third month indeed. So, okay, that's good that people are happy. So, today we have some nice talks to complement what we have already discussed last time. So we had in the beginning like several talks covering from the how quantum and AI can joint effort, the high performance computing, the applications in chemistry of high performance computing combined with AI and also quantum computing in general. The AI foundation models, how they can be used, AI in chemistry, and today we are gonna navigate two nice topics: the quantum AI agents and the computational modeling in quantum computing. So I'm gonna highlight the session quickly. So the program is gonna start by talking about the Alexandria Hackathon by Mr. Youssef Eldakar. He's the head of the International School of Information Science at Bibliotheca Alexandrina. And myself, we are going to talk about it. Then that will be followed by the presentation of Mr. Alain Chancé. He's the president of MolKet SAS. This is our startup that we co-founded in August last year. Quantum AI agents is a hot topic at the moment. And after this, it will be followed by a talk and also a mini lecture by Professor Ahmed Shawky Moussa. He's going to talk about the computational modeling in quantum computing. Okay, so we are going to now start with two things, talking about the Alexandria Hackathon and the potential course and certification by the Open Quantum Institute organized via Bibliotheca Alexandria, and Mr. Youssef Eldakar is going to present it.
Thank you, Dr. Taha. It's really nice that we are into our third edition. Thanks again for the help organizing the big effort. And of course, thanks to our speakers we have today, Alain and Dr. Ahmed Shawky. It's very good to have you. Thank you very much for taking time to deliver the presentations. So we mentioned, I think on the first edition, the idea of the hackathon, and the idea is now taking shape, and we have more concrete plans for it. So I just wanted to give the updated information that we have now. So we are looking at September 3rd and 4th and maybe 5th, depending on how the schedule turns out, as possible dates for as tentative or very much almost confirmed dates for the hackathon. That's September 3rd and 4th and maybe the 5th. Hosted at Bibliotheca Alexandrina in Alexandria, Egypt. And we are currently working on a website for this activity to hopefully be out soon. So for this hackathon, we are looking for interested participants who have the motivation and the drive to work on quantum computing and eventually go through the experience of a hackathon where they would work on real-world problems to find solutions for using quantum computing. So let me speak a little bit about the timeline. So I mentioned we are planning to launch a website for the event, and we are planning to open registration or actually the application window for people to apply to be part of the hackathon mid-April. And once that's open, we hope that we will receive many applications. Hopefully many people will be interested. And after that, there will be a review process and selection. So for those who would be selected, there is, since we're doing all of that as also collaboration with the Open Quantum Institute that's under CERN, there is a certification course. For that, I can share a link in the chat. Okay, so this is a simple document that has a little bit of information about this course. This certification course will be hopefully something to prepare the participants for the hackathon, and I think it's a nice thing that we can include this as part of the hackathon package. Again, it's offered by OQI, the Open Quantum Institute. Other than the course, Dr. Taha had plans for a hackathon before the hackathon. So maybe in June, maybe in July, something like that. You have maybe like a dry run version of the hackathon, or more of a national hackathon as preparation for the actual hackathon to take place in September. Again, we really are looking for people who are interested and have the motivation to take on this journey. And if you have any questions, please do share them.
Yes.
And one last thing I can also mention is the hackathon is hopefully will be a major milestone for people who are seeking maybe a career in quantum computing, because it's winners from the hackathon will also have the opportunity to be part of internships, international internships in quantum computing that will hopefully be offered by OQI and CERN. So that's all I have. Dr. Taha, if you would like to add anything else.
I think that's brilliant. Thanks, Youssef, for this nice intro about the hackathon. As Mr. Youssef have already mentioned about the dry out hackathon, I'm going to share the slides quickly. So previously, okay, so I'm now just getting the share button. Just a bit tricky to share. And as we tested it, Alain and I were testing it yesterday. So now yeah. Okay, so you hopefully are seeing now my screen. Now waiting for it to appear. Do you see it, or do you see the slides? Or?
Yes.
Maybe it's now much better, I think, hopefully. Yes. Okay, so we will have, of course, the International Hackathon, and this will be, we will start with a dry out hackathon. It will be a national hackathon, which also will be supervised by scientists from Egypt and abroad, also experts from abroad as well will be invited to join and to join the International Hackathon as well. The dry out hackathon, for example, could be supervised and also kicked off by professors like Dr. Ahmed in some universities and so on. And we have several mentors to help in that. And in the International Hackathon that will be held in September, we are going to have a formal committee where people will travel from Egypt to Alexandria, but also from other places as well to help in judging the presentations that would be prepared by the students and the groups of participants in this. So the details of the dry out hackathon is not yet prepared. It's we will just make a group for it, and we are gonna discuss it as well, how this is gonna proceed for the dry out hackathon. And the International Hackathon, all of these details will be provided by Mr. Youssef, because that's already will be solid. We will have a solid plan that's already organized with the Open Quantum Institute, and then we will have fixed dates and potentially fixed projects where the groups are going to work on. So together we have this course that will be offered by Open Quantum Institute as a certification course, but next to this we have our own Quantum AI Lab. This is a sort of running on weekly basis to introduce the basics of quantum computing and the quantum programming. It's now typically runs every Sunday, but apart from the holidays and formal holidays. For example, next time we are gonna have talks about Grover algorithm and some applications from the invited speakers and talented researchers in Egypt and abroad. And these weekly sessions are mainly held in dominantly in Arabic, so to make it easier for the followers. However, the monthly series are the ones that are held in English, so we can conduct these several presentations and so on.
Voice is lost, Dr. Taha.
So how about now, Dr. Ahmed?
Yeah, now it works.
Yeah, thanks a lot. Yes. We have this. We have the certification course, and this certification course, if you are motivated, please feel free to apply for it because it's very helpful and will put you in the mindset of the international hackathon that will be held in September. Also, it will give you a glance and a glimpse about how the projects will be conducted and also will be examined. So feel free also to apply, even if you are a beginner or you are expert, just only to learn also about the educational flavor of the course itself. And this will be helpful later when we have the series of hackathons. Okay, so this is for the Quantum AI Lab. So stay tuned, please, to follow more details. So now I'm gonna introduce the next talk, and this will be the Quantum AI Agents by Alain Chancé. So Alain is the president of MolKet SAS, and MolKet SAS is a member of two international networks, QEDC and QUIC. The QUIC is the European equivalent of QEDC. This is the American one. And MolKet is offering management consulting and AI services in quantum molecular dynamics, cryptography, neuromorphic computing, and also with cloud-based hybrid HPC and quantum computing platforms. Also, Alain is the founder and CEO of Quanta Alain Sassou and Alain Quant LLC. Those are business management consulting startups. He's also a Qiskit advocate and IEEE senior member, society affiliate of the American Chemical Society, for example, or the American Chemical Society, and also member of the Quantum Security and Defense. This is a group in UK, and also member of several board for institutes that are responsible for teaching professional certificates programs in quantum computing and quantum computations. Who's panelist in several panels, for example, in quantum and AI use cases, where we were together discussing about the potential and future of AI, and also he participated in several international conferences, and he was keynote speakers in many conferences, and he's a co-author of the book Quantum Chemistry and Computing for the Curious, illustrated with Python and Qiskit code. And he has many years in experience in major enterprise transformation projects, and he holds a master from École de Menil Saint-Étienne from France at 1981. Okay, so Alain, please feel free to present your presentation.
Thank you, Taha, for your great introduction. Now I'm going to just bear with me. I'm going to try and make the diaporama visible. Hold on. Okay, so I guess you can see my screen, but it's not the okay. So let me try again. Okay. So bear with me. It's always a challenge to get this to work. Okay. So right, I think that's it. Okay, so thank you for having me again. And today it's a very exciting topic. 3 words: quantum, can be quantum sensing as well as quantum computing, but also quantum communication, AI, artificial intelligence, and agents. So let's move on to the. We have a dense agenda, as you can see. So let's remind everyone what are AI agents. So it's a buzzword. So AI agents are systems or programs which are designed to perceive their environment, make decisions, and act autonomously. This is what defines an agent, being autonomous or semi-autonomously. And to do what? Well, to achieve specific goals. They are central to many applications of artificial intelligence, ranging from chatbots to robotics and complex decision-making systems. AI agents are increasingly being applied in chemistry, leveraging their ability to process vast data sets, understand complex concepts. Now, the meaning of understanding, it's still a hot debate, but it appears that they understand. And their added value is that they generate insights for various applications. And on the left-hand side, there is a nice image which I got from by Kishore Pandey's post. That's the credit. And so there are many different types of AI agents. Learning agents can be also utility-based agents and goal-based agents and so forth. And in terms of architecture, there can be single agent, multi-agent, agents that interact with humans. And well, what happened historically is that at the beginning, agents were just simulated using large language models with clever prompting. Instead of telling the LLM you are an expert in one particular topic, it was found experimentally that by telling the LLM, hey, you are a team of experts, then the LLM did provide some useful or more sophisticated responses. But it has evolved, and nowadays we have a bunch of multi-agent open platforms. There is one from OpenAI, but here we are talking about one which is still work in progress. It's from IBM Research. It's called BAI. So it's experimental open platform to discover, run, and compose AI agents from any framework. So that's what makes it interesting. It's framework agnostic. It can integrate AI agents seamlessly, no matter the language, the programming language, or the platform. You can build complex multi-agent workflows from simple building blocks. And there is a powerful agent catalog with integrated search. And in terms of languages, it supports both Python and TypeScript. So I provide a few links. So this is the one we are exploring at MolKet, and it looks really promising because it goes way beyond the initial large language model AI agent. You can basically with this tool, which is open, you can have a variety of agents. Okay, let's see. There is another hot topic which is called quantum robotics, and basically it's this. We are talking about quantum robots or Q-bots. There are robots which leverage the weirdness of quantum mechanics, and that can expand their scope and capability. We'll see example further down. So I've introduced AI agent, I've introduced quantum robotics, and guess what? Well, these fields somehow converge, and this is what we are going to explore in the coming slides. So a typical example, which dates back 2018, so it's before I would say the hype around the large language model or generative AI. So it's IBM Robo RxN for chemistry. So what is it? It's a cloud-based AI-driven, autonomous chemical synthesis robot. So it's built on the digital chemistry platform, which IBM released online since 2018. It's what it does. It assists humans, chemists, in discovering and creating new materials, particularly environmentally friendly enzymes, and it does that directly from the literature or the lab notes. So the way it works, a human, a chemist, all what needs to be done is to copy and paste from their lab notes paragraphs describing chemical procedures, and they copy that into a text box. And then Robo RxN plans a standardized list of actions. So in terms of lab automation, it's typically injection, temperature change, shake or swirl. And it translates these into machine-readable instructions, which are then fed to the automation hardware. And so the automation hardware, there can be a variety of different brands. Now, what's interesting is users can train RxN with their own data sets, using their own proprietary knowledge for customizing their prediction models. Since it has been introduced, more than 30,000 users have used it and performed over 5 million reaction predictions. So this is a practical example which illustrates the fact it has been in production for a number of years now. On top of that, there is a large language model, LLM chemistry agent, which uses the RxN as one of the tools it can use, not the only one. But the added value of the LLM is to bring or hopefully the more intelligence, and it achieves that by implementing a so-called chain of thought reasoning loop. So it's classical in the LLM arena. Chain of thought, as this approach has proved to be very successful. So as input, an expert will input as a prompt, if you want, something like plan and execute the synthesis of an insect repellent. Okay, so that's the input from the human, from the chemist, and then ChemCro starts by reasoning and planning, and selecting a tool from, this is where the strength comes from. There is a number of different tools which can be used, and then so there are two types of tools. There are general tools like very simply a web search or RxN, but also molecule tools. And so what that has achieved, ChemCro has autonomously planned and executed the synthesis of an insect repellent and a number of other exciting materials. And well, you can actually try it out on Hugging Face. I provide the link. So this is what we have seen so far is beyond the definition of an AI agent we have seen a tool which has been used for a number of years since 2018 for lab automation. But on top of that, a large language model which provides more sophistication in terms of chain of thought. Okay. So what we view from our perspective, which is, as you might have guessed, related to chemistry and quantum molecular dynamics, which are the expertise of MolKet, we see that and we provide quotes from Jackie Dari, who is the CEO of Google Sandbox AQ. The biggest breakthrough, we think, as Jack says, it won't come from chatbots, but it will come from artificial intelligence that models the physical world, not just language. And so Sandbox put forward the concept of large quantitative models. So instead of language, text, you have basically physical data. And then the idea is that it will transform industries by integrating physics, chemistry, and machine learning to solve real-world challenges. Now, this is in line with another perspective from well-known solution providers that one of the weaknesses of large language models is sometimes they hallucinate. With large quantitative models, with models which are fed with physics data, then physics laws can play the role of regularizer and help AI models to learn faster and generalize better. And so the growing trend is to properly combine data-driven, which has been field proven for a number of years, and physics-informed paradigms. So this is where we see the convergence of artificial intelligence with, I would say, field proven mainstream chemistry packages. Okay. Now we jump into something which is very promising, combining as input not just physics data, but guess what? Quantum data, and feeding that into AI and leveraging the power of high performance computing or supercomputer. It's the same. And this has been introduced by Quantinuum. They have announced a generative quantum AI framework, and it's a loop. So you can start in the loop with the AI that helps scope a problem which is dealt with by the supercomputer, and then that helps focus the work which is handed over to the quantum computer. But then the quantum data which comes out of the quantum computer can then be processed by AI. Now this interesting view is also has also been demonstrated by a team from Microsoft Azure Quantum, and they have demonstrated, or at least they claim they have been the first to integrate high performance computing, quantum computing, and AI for end-to-end quantum simulations of a chemical system. So there is a flow chart on the left, and in that flowchart, they explain that they start with classical high-performance computing calculations, which are fairly expensive, of course. And then they prepare the work for the quantum computer, which is then which is very focused, and from the quantum computer as output. The measurements, the expectation values, they get quantum computing data output, which is post-processed with classical AI. And this is something we put forward from MolKet. The idea that it's challenging, and it takes a lot of resources to run the HPC calculation and the quantum computing calculation, and as output, hopefully one gets high quality data, and where AI and especially surrogate models are really helpful is that they make it possible to learn from these high quality data points which come out from the quantum computing, and then they can predict within a certain space the data for of interest, and that is a synergetic combination of the three. Okay. So there is actually a reference from IBM, Cleveland Clinic, and RIKEN, where this has been success. It's called sample-based quantum diagonalization (SQD) for simulating chemistry with so-called quantum-centric supercomputers. So that's the terminology used by IBM. And so SQD, it's a classical post-processing technique which acts on samples, that's what I explained in the previous slide, obtained from a quantum circuit after execution on a quantum processing unit. Now, what is really impressive, and this is from IBM themselves, is that on today's quantum processing unit, it would take 3 million years, I repeat, 3 million years to model an iron-sulfur cluster. Now, with IBM's Heron processor, which is the latest and greatest quantum processor from IBM, and RIKEN's Fugaku supercomputer, or high-performance computer, running this sample-based quantum diagonalization post-processing technique, the same model can be achieved in just 2 hours. So you see, this is it works, it's operational, and it can achieve something which would take 3 million years on a quantum processing unit using the variational quantum eigensolver. What's important to realize, it's not just those tools, putting them into a workflow and pressing a button. There is an awful lot of work by a multidisciplinary team behind the scene. So this is really important. And this is from Dr. Robenold. He said multidisciplinary collaboration was essential to achieving this framework, combining the RIKEN supercomputer and the IBM Heron processor. And I quote, he said, our team's expertise ranges from computational biology and chemistry, structural biology, software and automation engineering, experimental atomic and nuclear physics, mathematics, and of course, quantum computing and algorithm design. So it took the knowledge from each of these areas to create a computational framework that can mimic one of the most important processes for human life. And they succeeded. They claim that their quantum classical hybrid framework, the initial results outperform both a classical physics-based method and AlphaFold 2, which is a very successful deep learning model from Google. So I think this is really important. It's a huge challenge from in a human dimension to make this work. Okay. Just this to say that IBM and Pascal is a French startup. They have a very interesting design, and actually they have installed a bunch of their computers. It's neutral atoms. So it's a different approach from IBM. IBM use superconducting loops, and Pascal they use neutral atoms. But the two have partnered because they believe in the quantum-centric supercomputer approach. So together they want to ensure that this framework, quantum-centric supercomputer, is open and agnostic to the hardware. So that will create more value. Okay. Here I give examples of something different, but nevertheless very, very important because it's in operation. It's a combination of AI and quantum sensing. So AQNav, it's a sandbox AQ's breakthrough real-time dual-use magnetic navigation system, dual use because it can be for civilian or defense, okay, powered by AI and quantum magnetometers. Quantum magnetometers are a type of quantum sensors which are very, very sensitive. And their IQNAV, the big advantage is that it can work when GPS are jammed or spoofed. Okay, so the way it works is that they have measured the Earth crustal magnetic field, and they have created kind of a three-dimensional map, and then with proprietary AI algorithms in real time, because this is designed to be put in, say, a drone or a plane or a submarine, then IQNAV can deliver an unjammable, all-weather, terrain-agnostic passive technology to position the unit which uses this IQNAV. There is another competitor, but again using quantum sensing. Lockheed Martin has been awarded a contract by the US Department of Defense Innovation Unit to prototype quantum-enabled inertial navigation system. Okay, so these two examples to illustrate that today we have in production at least one example there, a quantum sensor, in that case a quantum magnetometer, combined with artificial intelligence. Okay. Something recent also, very promising, an operating system for executing applications, distributed applications on quantum network nodes, which makes it possible for developers to focus on creating applications without having to deal with the complexities of physics to learn the ins and outs of various quantum processors. So this has been put forward in the recent past. So at each node, the only thing which is needed is quantum communication, for example, entanglement generation, and classical communication. Okay, I won't go into details, but it's nice to see that this operating system makes it possible to focus on delivering value, creating application, and the complexity of putting together a network of quantum nodes is taken care of. Okay. Now, something really recent as well, very promising, a cryogenic in-memory computing, which reduces latency between AI agents and quantum processors. So that means that it's possible to have AI accelerators, classical, which can operate just a few centimeters away from quantum processors. And that significantly reduce the amount of time it takes for the two to communicate with one another. So it's very promising to integrate AI and quantum processing. Okay. Now the big picture is to integrate quantum sensing, quantum communication, quantum processing, and AI, and this has been put forward a number of years ago, actually, by Robert Huang, who is a world-class expert in quantum learning. Quantum learning is a field of study that has already demonstrated, at least in theory, that quantum processors can learn from quantum data more effectively than could be achieved classically, which is no surprise. So this is an example, an illustration on the left. So quantum sensors being fed into quantum processing units, and one piece which is still a challenge, we don't yet have decent quantum memory, at least for processing. We only have quantum registers. And so the other picture is quite interesting. It's from a paper which has a very nice title, I find. Do qubits dream of entangled sheep? And so it's a paper which has studied how a quantum network could be built with different quantum agents that communicate via quantum communication channels and they interact with the world via quantum peripherals. And so on the illustration on the left, we can see a nitrogen vacancy NV center in a diamond. So it's a quantum type of quantum sensor that fits into a quantum computer A, which interacts with another quantum computer B, and also a quantum device. Now, what's interesting is that this kind of architecture, in order to study it theoretically, they had to invent beyond what is the mainstream approach of quantum physics. In particular, because they had to redefine what is meant by measurement. Because in the mainstream quantum physics, a measurement involves a human, okay? But in that case, you can have basically it can be all quantum all the way, and so basically what that means is that that leads to experiments that could help quantum physicists refine the quantum physics, quantum mechanics theory, which has so far not been disproven, but there are still challenges interpreting what does a measurement means, and this is an example without a measurement. Okay. So to conclude, what we are trying to achieve at MolKet, we aim to make chemistry simulations easier and faster with artificial intelligence, quantum computing, and high-performance computing. So we provide management consulting and artificial intelligence services for quantum molecular dynamics, cryptography. By the way, in May, I've been invited to make a presentation for the ICCCAS in Wuhan, and the topic is quantum permutation pad with Qiskit runtime (QPP). So that's quantum permutation pad is a protocol for sending information in a secure way, which is part of cryptography. We also are exploring neuromorphic computing and all that, leveraging cloud-based hybrid HPC and quantum computing platforms. We also offer services, consulting services for training artificial intelligence on data sets from fields such as chemistry, biology, material science, and cosmology. Okay, so just give an example. This is something which is made public. We have published that on MolKet's GitHub. And it's about a topic Taha knows very well because it's a topic he studied during his PhD work. So it's the collision of helium and carbon dioxide, and it's a very interesting topic for in cosmology. And so what we have demonstrated is that using a Fortran subroutine that computes the interaction energy between the helium atom and the CO2 molecule at 4 Jacobi coordinates, we managed to train very accurately a model using out of the box Julia surrogates package. Julia is a programming language which is as cool to use as Python, but in terms of performance, because it's interpreted and also compiled, it fares well against Fortran or C++, and so the advantage is that instead of writing something in Python and then rewriting in Rust with Julia, you only need to develop your program once, okay? And so I provide the link to our GitHub Jupyter Notebook. And so what we mean is that we are in a position to train an AI model from data which comes from the output of a HPC plus quantum computing calculation, and so this illustrates the concept of illustrated with the work by a team at Microsoft and also IBM. Okay, this concludes my presentation. In the deck of slides, in the chart, you will find an extended bibliography and also a glossary of terms for those who discover what AI is. So these are useful glossary, which comes from a very good course from IBM, which is Generative AI Introduction and Applications. Okay, so that's it from me. Thank you for your attention, and I'm open to a question whenever there is a question and answer session. Okay.
Yeah, we'll just now have the questions at the Q&A session at the end. So please write them in the chat, and then we are gonna discuss them at the last half an hour of the session. So write them before you forget them. So thanks, Alain, for the nice presentation and outlining in a very clear way the idea of the quantum AI agents and why we need it and how we can bring value from it, and also what we are currently doing in MolKet and also the MolKet projects that we are currently working on. So for everyone, please feel free to ask. Also, the presentation will be shared with you at a later moment. So you can also revise them with the recordings, and then whenever you have questions or you have something you want to explore, please feel free to reach out to us. So yeah, thanks again, Alain, for the nice presentation. Yeah, for Dr. Ramadan, yeah, please write the question and then we will come to it in the Q&A session. Yeah, so our next speaker is Professor Ahmed Shawky Moussa. Is also Dr. Ahmed is well known in HPC community and very famous person. Also was one of my teachers during the undergraduate study, also as well at American University in Cairo. So Dr. Ahmed is associate professor of computing and computational sciences at the Faculty of Computers and Artificial Intelligence, Cairo University. He's also founder and the head of the HPC R&D lab. He also served as HPC director at the Applied Innovation Center of the Ministry of Communications and Information Technology, where he founded and led the first HPC system at MCIT. Also, Dr. Moussa's main field of expertise is high-performance computing and the integration of various AI paradigms to create computationally intelligent HPC systems in both academic and industrial worlds. His academic achievements also included contributing in innovative applied solutions and incorporating them to improve the HPC systems performance and solve scientific problems involved in modeling of larger scale, complex, dynamical, and uncertain systems. So in the industry, he led mega multidisciplinary projects and in multi-sector applied projects from R&D to innovation using HPC, AI, and other emerging technologies. He also has a US patent and co-founded and led several national entities and serves as expert a consultant for many national and international institutions. So welcome, Dr. Ahmed, and please feel free to share your presentation. I'm going to stop sharing my screen now.
Thank you very much, Dr. Taha, for the introduction. Thank you all for attending this session. And thank you for getting together again, Engineer Youssef Eldakar, Alain. I miss you all. I'm also not that good at sharing screen on Meet, Google Meet, but I think I will share the entire screen and then move to the presentation.
Right. So, Alain, I found a trick to, if you would like to share it from a tab or from a drive or from online, you can share it, or you can try to, for example, have all the screens in front of you and in the same desktop, and then choose this one. Because if you make a slideshow, it will move it to another desktop, so the Google Meet will not detect it easily.
I tried to share the entire screen, but it didn't work. Let me try it again. If it didn't work, I will try something else.
Yeah, that's an annoying problem. Alan and I were struggling with it yesterday, but luckily yeah, we could find this tab at least in Windows.
Yeah, I'm more familiar with Zoom actually than Meet, but I think I have to learn it anyway. Let me check where the presentation actually is. The HPC QC, okay. It shows only the tabs. It doesn't show the other programs. I don't know why.
So there is a three like titles. One of them called the tabs, one of them called Windows, and the entire screen in the share.
Yeah, the entire screen didn't work. So let me see if.
But if you use it from Safari, it is a different story, because also Safari has another suppression layer to Google.
Actually, I'm using it from Chrome.
From Chrome, yeah. From Chrome, it gives this little window where you can have, for example, tabs, Chrome tabs, Windows, or entire screen.
I think it's sharing our meeting.
Yes, I think because of yes, now this is sharing the same tab. But what happened if when you click on the share, don't you see this like little window where they say Chrome tabs, Windows, entire screen?
Yeah, Chrome tabs, window, and the entire
Maybe
screen.
if you click on window, do you see the presentation in those windows?
No, I see our meeting, only our meeting.
So maybe the presentation now, if you are using a Mac, if you go up, then you will see the desktops. Maybe the presentation now went to another desktop. So if you click on control and yes, on the control and the upper arrow, the upper arrow from the keyboard. So you click on, then it will bring for you the all desktops that you have. And maybe the presentation has went to another desktop.
Okay, let me see this.
Yeah, by clicking on control and the upper arrow. Or also you can open the slides in the tabs itself as PDF and then share the tab from there.
Dr. Taha, excuse me.
Please.
So if I may help, Dr. Ahmed, دكتور احمد انت ممكن تشغل برزنتيشن على اللابتوب عندك عادي، وبعد كده اللي هو السهم الارو الفوق ده بتختار حضرتك اللي هو الانتاير سكرين، هيشتغل عادي مع حضرتك مباشرة. يعني انت بتشغل برزنتيشن بتاعت حضرتك عادي على اللابتوب عندك، وبتختار الانتاير سكرين مع الشير طبعا هيشتغل مباشرة يعني. I think so يعني.
Yeah, potentially Dr. Ahmed is now restarting his Google Meet.
المحاضرة ديت معلش يا دكتور طه متسجلة، يعني المحاضرات اللي احنا خدناها المرة اللي فاتت اللي لسه جاية دلوقتي حالا هتبقى مسجلة هنعرف نشوفها تاني، أو برزنتيشن دي بالسلايدز دي بتاعتها هتبقى موجودة؟
Yes, all of this presentation. So that's because I'm just answering because now the session is in English, but I understood the question. So
Okay.
yes, everything is in English. Everything will be recorded, and also including the slides. It just need to be shared. So after some editing to remove the silences and everything, so that will be shared on the iCafé channel.
Thank you, doctor.
Okay, so you can consider it as a pause of 5 minutes. Yes, Dr. Ahmed is back. That's nice. So, Dr. Ahmed, when you make the slideshow, or you can also make it smaller, and then you can select this one. Yes, now this is the tab, and then presumably if you open it, yes, where is the presentation? Yes.
Okay, I hope it works now. Can you hear me?
Yes.
Okay.
Yes, we see your desktop, and also the presentation when you clicked on it. Yes. Yeah, now we see the PowerPoint.
Okay. Finally.
Yeah, it's on the full screen and everything works perfect.
Okay. Thank you for the patience. Well, I will not take as much time as set on the schedule because I was surprised that I was given nearly 2 hours to talk. And I have to admit that I didn't have time to prepare the entire talk I wanted to present. So I only made the start of what I wanted to lecture about today. And perhaps I will need one or at least one, preferably two more talks to finish this large complex topic. When we're talking about computational modeling of quantum computing, the origin of that comes from the concept of modeling itself in science in general and in physics in particular. The whole science of physics and probably all other sciences, but I don't want to get in there with the presence of the experts, not to miss or mess with anything. But let me talk about the science of physics. Physics itself is about modeling. So when we build the science of physics, we actually build models. Sometimes we are able to verify these models with absolute certainty, but those are not often. But in many other cases, we have evidences, we have a model that works for interpreting and developing the science itself until it proves either wrong or insufficient. Sometimes this happens frequently. Sometimes it takes hundreds of years for this phase to pass on to the other. Let's take some examples. At a certain point in the old days, they thought that logically, since we have big objects in the nature, those objects are breakable into smaller objects. So if we keep breaking them into smaller parts, we must, by logic, or by the logic that we thought at that time, at a certain point we will reach a small object, a very, very small object that cannot be broken further. And this would be the origin of all the material in the world. And that object by name was called the atom. It took thousands of years to realize that we have an atom that can be broken. So first we got into the molecules, and then we got to the atoms, and then we realized that even this atom, which we thought is the real essence or the real origin of the universe, it can be broken into smaller parts. And those smaller parts could be broken further into smaller parts. When we try to see the construction of this atom, how it is constructed, we had evidences that it has a bulk of material and smaller other materials around somewhere. So we built, after the original model that we thought would work, which is the atom, put atoms together, you build the universe. So now we want to see how to build the atom, because the atom is breakable. So we thought that there is a big substance or big something and has smaller somethings embedded into it. And we thought that this is the structure of the atom. That big something was the nucleus, and those smaller things were the electrons. At a certain point, we ran an experiment, and then we realized that it cannot be that way. It turned out that this model, it is a model. So this model is wrong. It was okay when we started it, but by running some experiments, it didn't hold. So it must be wrong. So we started thinking of another model, and we started realizing that those smaller things are moving. They are not fixed, like the raisins on the cookie. So they're moving. So we started thinking of the model of the solar system. So instead of the sun, we have the nucleus, and those smaller things that we call electrons are orbiting around this nucleus.
Yeah, so Dr. Ahmed, we are now seeing the cover slide of your talk. Is it the
Yes,
one that you
yes,
are
I'm still making the
okay.
introduction.
Yeah, great. Yeah, great.
Yeah,
Yes.
Because the other slides are not too many. I'm talking about I didn't need slides for this, or I didn't think I needed slides for this introduction, because we all know it. I just wanted to use it as a preface to get into the topic.
Yeah, no worries. We just a question about if the slides are moving at their sides or not. Yeah.
No, when I move the first one, I will ask if it is okay. So we thought that these electrons are orbiting around the nucleus, and that was okay for a while, not long while, for a little while, and then we realized that we ran another experiment, and we realized that it cannot be orbiting, especially after Heisenberg and realizing that we cannot play with the electron the same way we play with the solar system objects. So we started thinking of another model, and it kept running until we reached the quantum state of the atom and the subatomic components of the atom. As you can see, in all these, we are doing modeling. So we are building the science by modeling. Is this going to hold forever? We don't know. We hope it will hold forever. Other things took longer to change. Like, for example, when Newton modeled the physics of gravitation, it was holding for about 200 to 300 years until Einstein came and started questioning Newton's model. Is this he didn't question the gravitation itself, but he questioned the model that Newton built to explain or to understand the gravitation. Einstein was not convinced that there is a force between any two bodies that get them to attract each other or get them to stuck to each other unless another force is separating them. He didn't like that. But this is the model that we had, and it's the model that was able to explain the movement of the planets in the solar system, the movements of many things. We were able to explain it and actually calculate it accurately. It failed in some rare cases, but it's not time to talk about them. But overall, it was working fine. But it was not logical to Einstein. So now the science is not wrong, but the model was not satisfactory. So again, when we are talking about building science, we actually build models. So the question to Einstein was, okay, so this is the model that Newton came up with, and it's the one that we have. If you don't like it, do you have another model? And then he said, yes. And he came up with a model of the curvature of free space. You know, the famous experiment, imaginary experiment. If you have like a bed sheet and you hold it from all sides, it is two-dimensional. And then if you put like an iron ball in the middle, the curvature will change. And then if you put a smaller one on the side, it will run into the big one. It doesn't mean that they attract each other, but they just roll into each other because of the curvature of free space. So again, we are building models. So when it comes to quantum physics, we are building models. And now we are running into the problem of trying to connect the world of quantum physics with the world of classical physics, because they have to work together to solve problems now. HPC until now is built on top of classical physics, classical electronics, but quantum is building on quantum mechanics. So can we understand quantum mechanics using classical mathematics? Now, this is okay. Now I changed the slide. I hope you all can see it.
Yes.
Okay. So now can we understand the quantum mechanics using the classical mathematics, because these are the ones used for the HPC systems so far. Overall in mathematics, we can go with analytical methods or numerical methods. Here is a big debate because I personally tend to contradict with most scientists who think or at least claim that analytical methods are the accurate ones. And when we are not able to come up with analytical solution because these are the accurate ones, we come up with numerical methods to come up with approximate solutions. Actually, I contend that it is the opposite. Analytical methods work with straight lines, perfect spheres, perfect circles. It's the geometric shapes that are human-made, man-made geometric shapes. But what in the nature is actually that perfectly geometric shape? Nothing. Actually, nothing. It is that perfection of geometric shapes is the simplified version of these shapes that we are not able to build or deal with. So we try to think of the Earth as a perfect sphere, but it's not a perfect sphere. And it is not like another geometric shape either. It is close to a perfect sphere, but it is not perfect sphere. Nothing in the nature comes in the form of a perfectly straight line, or perfectly any geometric shape. So this is why I claim that the real science is the science solved by numerical methods, and it's the analytical methods that are approximate, not exact. It is just that for hundreds of years, or maybe for thousands of years, the human people always thought that the perfectly shaped geometry are the ones that are the target, the ones to calculate, and we are not able to calculate them. We try to come up with numerical methods. I tend to claim that it is the other way around. So now, if the numerical methods in my claim are the exact, and the geometric or the analytical methods are approximate, regardless of whether this is correct or the other claim is the correct one. Now, which one should we use, analytical or numerical methods, when it comes to modeling quantum mechanics? In fact, it turns out that in quantum mechanics, there are very, very few problems that can be dealt with analytically with an oversimplified system. I cannot think of anything other than the three that you can see on the screen: the quantum harmonic oscillator, the particle in a box, and the hydrogen atom. I cannot think of other examples that can be dealt with analytically. Other than that, all quantum mechanics problems must be dealt with in numerical methods. But which numerical methods? Okay, now let's start with first with the simple one, or the most famous example of quantum mechanics is the Schrödinger equation. And let's see how we can model Schrödinger equation to understand it, and see how it models the quantum nature of the particle. To do that, it is challenging, as we will see probably in the next lecture, not in this one. But let's start with simplifying the system. We will oversimplify Schrödinger equation. We will consider the time-independent Schrödinger equation. The three equations on the screen are the same. There are three notations, three ways for notating or annotating the Schrödinger equation, but they say the same thing. The first one is generic, talking about this one as an operator, but then we specify here this operator into the second derivative. So the three are basically the same. If we try to solve this numerically, we will run into several problems. First of which is that we will have to deal with a complex function involving complex number. where the square root, modeling the square root or considering the square root of -1. This is the first problem we'll deal with when we consider numerical methods. The second problem is that we will have two unknowns in here, both the total energy and the psi, the wave function. They are both unknown, and we need to find them out using the same equation. So with the numerical methods, we will face some challenges. Okay. If we consider this and try to solve it, we also have to understand that solutions exist for specific values of E. E here is not continuous. It cannot be found for anything. This is what the quantum mechanics experiments have proven, and this is why we have quantum energy levels. So this is the origin of the discrete energy levels in quantum mechanics. Okay, now to understand it, let's start with an analytically solvable example. To be analytically solvable, it must be oversimplified as stated before. We will consider a particle moving in free space. Moving in free space anywhere, everywhere. That means that the potential energy is constant. So V equals 0. And we will oversimplify it also by considering the space as one-dimensional. So in this case, psi is the psi of x without any interference from any other objects. In this case, the stationary or the time-independent Schrodinger equation becomes as we can see it in here. So this is after the oversimplification of the system. Of course, this is rather easy, and this is the general solution for it. Psi can be found by A, which is a constant, the exponential of I kx, and k here is also a constant. With this general solution, we can verify it. It's provably correct, and we can get E rather easily, as you can see. But in this general solution, we have a plane wave function where the wave vector k equals 2 pi over lambda. Lambda here is the wavelength. We can see starting to talk about the oscillation in here. Some oscillation is going to take place. K is also closely related, very much related to the momentum, because the momentum equal hk. So they are related in an equation. So we start to see that some other components must come into the game. In this example, there is a solution for any k, which actually contradicts with the quantum mechanics theory, because we should not be able to find a solution for any k, because we know in quantum mechanics or quantum theory, energy is quantized. So we have quanta, certain areas where we can find the solution, and in other area we should not find the solution. So the energy here will not be quantized, because you can see here the total energy is related to k, and k is continuous. So E is continuous. That means that this is still an incomplete model. Notice that we are trying to build a model for the quantum world. We are now building together a model as Schrodinger did. So now the model is still incomplete. Something is missing. Now, the model of quantum mechanics, we all know that it is probabilistic. And the complex conjugate of psi and psi together form the probability of finding a particle in the region dx. Now, recall that until now, dx was everywhere. It was infinite. So let's keep it that way for now. But since this is probabilistic, the integration over that must be normalized. So the total probability must be 1 from mathematics and from probability theory that we know before that. Now we have a problem. This is the wave function. Now, if we use this wave function and apply this normalization using this equation, then the complex conjugate of psi and psi will equal to a square. This integration will result in a square times the integration over dx. But free space means, again, I just said that dx is infinitely large. It's everywhere. So if dx is infinitely large, then a must be infinitely small. Something is wrong here. It cannot hold mathematically. So we are trying to put ourselves now, by the way, in the mind and the heart of Schrödinger when he was trying to develop his equation, trying to develop his theory. So we need to fix this. How can we fix this? First, let's change our concept about dx. Dx is not everywhere. So x, let's confine x in a box. It's not a real box, but it's a box where x is limited by a value from minus L to plus L. So a certain value plus or minus. This will solve the problem of x being infinite. So for the magnitude of x to be less than or equal to L, then the potential V here must equal 0. And in that case, I mean that 0 is going to be outside the L limits. In that case, inside the box, psi will be a exponential ikx, which is the previous slide, which is good. Okay, now we solved part of the problem. Now for the other part outside the box, V is infinite. But E, the total energy, cannot be infinite. And that means that outside this box, psi equal 0. What does that mean in English? It means that we changed the model in a way to make psi have the actual value within certain limits. Outside of those limits, it is equal to 0. It means, what does psi in English mean? It is the probability of finding the particle outside of this confinement. And we all know that this is how the quantum theory works. So outside of the limit, the probability of finding the particle is 0. Within this limit, we have the probability of finding the particle. So now we are getting close, but still not final yet. Now, since psi is supposed to be a continuous function, then these are the two equations. We will have two equations instead of one. One for psi plus and one for psi minus. One for the psi and one for the conjugate of psi. So with these two functions, when we apply them together, now we have what we can call a standing wave. It is, for those who are not physicists, standing wave is like the waves constructed from a vibrating string. If you pluck a guitar or a harp or any string, you see standing waves. There is a big wave all over the string, and there are harmonics, smaller waves that are in place. They are standing, they don't move, but they are vibrating. Now recall that Schrödinger equation is a linear equation. That means that the sum of the solutions to this equation is also a solution. That means that we can have more than one solution. Several solutions can satisfy this system if we add those two equations together. And this is actually what the experiments proved. Now these are these are the lowest 6 states out of the wave function out of Schrödinger equation. Now, these two functions to be correct, they require that K plus equal these specific discrete values, K plus and K minus. So now it looks like K, according to this model, must be discrete. So the model that we had before, where K was foundable and calculatable everywhere, was incomplete. Now we are getting into the complete one, K plus and K minus. From this, we can see that K is discrete, and these are the exact values that can be found for K. Now that K is discrete, since E equal H squared K squared over 2M, then E also must be discrete. And this is where we find the beginning of the quantum theory modeled by Schrödinger. What did we do now? What we did is that we did not read and we did not use Schrödinger equation. We built it to model the physics of, or the beginning of the physics of quantum mechanics. I have to admit that I started late. I wanted to move further to the time-dependent Schrödinger equation and then show how to model this with a classical computing and classical computers and HPCs, and then start exploring the relation between the quantum world and the classical world when it comes to computation and modeling. But I started late and I stopped with this part. So in the next lecture, I hope I will have the chance to introduce the time-dependent Schrödinger equation and the modeling in programming of that model, and see how we can use the classical HPCs to model quantum systems. Because this is one of the main uses of HPC now. Quantum computers are sometimes unreachable. We cannot get them easily. Sometimes they are not yet in a state to be of true world applications. So what we can do is to simulate them to get the results. We cannot wait until we have a working quantum computer on real world problems to play with these things. So we simulate them on HPCs, and this is what I wanted to get into through this journey, starting with mathematical modeling of the quantum computing theory. Please accept my apology for not going on as long as expected, and we hope that the next time we will finish this topic. If not, then in the session after. Thank you. I cannot hear you, Dr. Taha.
Oh, yeah,
I don't know if...
Yeah, I forgot myself muted. Yeah, so thanks very much, Dr. Ahmed. No worries. I think that's a very good step. Thank you a lot for paving the way. I think that's will be a very good first lecture in a series of lectures to cover the modeling in quantum computing. And this is also complementing the monthly series that about now we see, for example, what Alain has presented, because he is now expert in doing, for example, the quantum AI agents and so on. And then now this is what we see from the industrial perspective. Industry is moving very fast, but how we come from the fundamental layer to this, like how the modeling is really incorporated, and how it is designed and how it's translated to computers. So I think that's a very nice lecture to pave the way for a series of lectures to cover this topic. So thanks very much. I'm gonna summarize the talks briefly in a few minutes in English and in Arabic before we move on to the free discussion. And I also have one or two announcements to tell about. So the first talk has been introduced by Alain Chancé. I'm gonna give the Arabic summary now. كان التوك الأولاني كان معمول من ألان شانسي، هو طبعا يعني شريك معايا في الشركة بتاعت مولكت، هي متأسسة في فرنسا، وهو قدم موضوع مهم جدا في الصناعة وغاية في الأهمية، وهو فكرة استخدام الذكاء الاصطناعي او الاي اي اللي هو بيتجمع مع الكوانتم او التكنولوجيا الكميه، وازاي ده مهم جدا في المجالات الخاصه بفهم الداتا. يعني ازاي نعمل نموذج ذكاء اصطناعي يقدر يصمم مركبات كيميائيه ويدرسها وفي نفس الوقت يطلع الخواص بتاعتها، ودي حاجه مهمه جدا للصناعات الدوائيه، بس كمان في صناعات المواد عامه، في الماتيريال ساينسز والحاجات دي كلها. وهو كمان قدم يوز كيسز كتيره، قدم تطبيقات كتيره قوي مختلفه لشركات كبيره. يعني كان الهدف كمان من العرض التقديمي ده كان هو كمان يتم تقديم ايه هي الحاجات اللي الشركات الكبيره العالميه كانت بتستخدمها، وفي حاجات كتيره اوبن سورس يعني مفتوحه المصدر فممكن استخدامها، بس لازم طبعا شغل جامد عليها ويتفهم، زي مثلا الشغل بتاع IBM وفكره السوبر سنتريك كوانتم كومبيوتنج، ازاي دلوقتي ان الحوسبه الكميه انتجريتد مع الهاي بيرفورمانس كومبيوتنج مع الحوسبه الفائقه، وازاي الاثنين دول مع بعض كده عاملين سينرجي كويسه جدا، وممكن يتم استخدامهم في عمل حسابات على الحاسب الكمي المتاح الحالي. الحاسب الكمي الكفاءه بتاعته مش عاليه، فممكن ياخد سنين طويله، حتى IBM بتقول انه ممكن ياخد كم مليون سنه عشان يعمل حسبه لكلاستر معين من بعض المعادن. ولكن لو هو الحاسب الكمي مع الحاسب العادي اللي هو السوبر كمبيوتر اشتغلوا سوا هيعرفوا يعملوا شغل كويس، والحسابات دي يتم اختصارها بدل ما تاخد ملايين السنين على الحاسب الكمي لان عدد الكيوبيتس صغير، لا هي ممكن تاخد يومين او 3 باستخدام التكنيك ده. وكمان ان الكوانتم AI او ان الذكاء الاصطناعي ممكن يستخدم في التدريب بتاعه قوانين الفيزياء، فبالتالي لو تم تدريبه على بيانات طالعه من مولكيولز من جزيئات ومن ذرات وكده، ده هيحسنه تماما وهيخلي ان يبقى فيه زي سيلف كوركشن، يعني في تحسين تلقائي موجود، وده جاي نتيجه ان قوانين الفيزياء اوريدي النموذج الذكاء الاصطناعي اتمرن عليها كويس، فهي بتصحح نفسها وكده يعني. نيجي للتوك الثاني. التوك الثاني كان الدكتور احمد، كان طبعا دكتور احمد اتفضل بقى، ممكن لو تقدم تلخيص يعني if you would like to present a summary in Arabic for your talk.
تمام، شكرا جزيلا. هو التوك كان المفروض يعني يربط الكمبيوتيشنال موديلنج ما بين الكلاسيكال والكوانتم كمبيوترز. وفي الكلاسيكال طبعا خلاص احنا بقينا في الحاله دي لازم نكون بنتكلم عن الهاي بيرفورمانس كومبيوتنج او الحوسبه عاليه الاداء. انا حبيت الحقيقه ابتدي من الانترودكشن او من تقديم فكره الموديلنج اتسيلف، لان احنا احيانا يعني بعض الطلبه في البدايه بيعتقدوا ان الموديلنج يعني ده الجزء بتاع ماثيماتكس وبروجرامينج علشان نحل مشكله الامتحان او مشكله حاجه زي كده، انما هو في الحقيقه الموضوع اعمق من كده. هي الفيزيكس الفيزياء عموما عباره عن مودلز، يعني احنا بنحاول نشوف الكون اتخلق ازاي، فبنلاحظ شويه حاجات ونبتدي نبني موديل بناء عليه بنطلع بثيوري مثلا زي البيج بانج ثيوري. دي ال يعني نقدر نقول الموديل اللي لحد دلوقتي احنا بنعتقد ان هو ده الطريقه اللي اتبنى بيها اليونيفرس. جت منين؟ جت من اننا علم الفلك عموما علم نسبيا جديد، يعني بقى له 100 سنه ولا يمكن اقل، فاحنا ملاحظين ان الكون بيكسباند، فاحنا بنقول طيب لو نمشي بقى بالعكس، ما دام الكون بيكسباند، طيب لو رجعنا بقى لورا في الزمن يبقى كان اصغر كان اصغر كان اصغر كان اصغر، فبنيجي لحد ما نقول يبقى هو جه عليه اكيد وقت كان عباره عن حاجه صغيره قوي 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 قوي، وحصل زي نوع كده من الانفجار فابتدى يعني يكبر وما زال بيكبر لحد دلوقتي. هل الكون اتبنى فعلا كده؟ ما نعرفش، انما ده الموديل اللي احنا واصلين له دلوقتي، وابتدى اليومين دول بالفعل يعني يظهر دلائل وثيوريز بتدل على موديلز مختلفه. وقدمت موديل تاني برضو بتاع الذره اللي افتكرنا في الاول ان هي عامله زي الكوكي والالكترونز دي عامله زي الزبيب كده عليها، وبعدين عملنا تجربه اكتشفنا انها ما تنفعش تكون كده، ده الزبيب ده اكيد بيتحرك. فقلنا طب بيتحرك ازاي؟ ففكرنا في الموديل بتاع المجموعه الشمسيه، قلنا بيتحرك كده حوالين النواه زي ما الكواكب بتتحرك حوالين الشمس. وبعدين طلع برضو ده مش صحيح، فابتدينا نفكر في الالكترون كلاود. يعني هو بقى بيتحرك حركه تبدو او قد تكون يعني شويه بالنسبه لنا احنا عشوائيه، انما في ليفلز مختلفه، ودي اللي بنسميها بقى الانرجي ليفل. فده الموديلنج، ده بناء الفيزيكس. فعشان كده كنت عايز بس اقول ان لما نيجي نعمل موديلنج لحاجه حتى احنا عارفينها، الموديلنج ده هو ده اصل الساينس من الاول. احنا مش بنحاول يعني نحط حاجه احنا عارفينها في صوره ايكويشنز وبس، لا ده هي الحاجه دي وهي بتتعمل، هي بتتعمل كده اصلا يعني. فابتدينا نحط نفسنا كده مكان شرودنجر وهو بيحط الايكويشن بتاعته، كان عايز يعمل حاجه تموديل الاكسبيرمنتس اللي ظهرت في وقته واللي استنتجوا منها او اللي استنتج منها الكوانتم ثيوري. وابتدينا من اننا نحاول نعمل سيمبليفيكيشن للموديل على قد ما نقدر، خليناه وان دايمنشنال، خلينا افترضنا ان الالكترون ان فري سبيس في افري وير. وابتدينا نشوف ان لما بنحط الافتراضات دي في حاجات بتفيل، في حاجات بتطلع لا مش مظبوطه، زي ما حصل كده مع الاتوم ثيوري. في حاجات بتتغير فبنضطر نغيرها، ابتدينا نغيرها لحد ما وصلنا لمرحله ابتدينا نكون منها بدايات الكوانتم ثيوري، ان فعلا عندنا انرجي ستيتس، عندنا انرجي ليفل، والانرجي ليفلز دي دول ديسكريت، والالكترون كان نوت بي فاوند ان بتوين، هو يا في الستيت دي يا في الستيت دي، انما ما عندوش ترانزيشن كده ما بين الاثنين. وده اللي ماشي بيرفكتلي مع الكوانتم ثيوري اللي احنا عارفينها دلوقتي. اللي فاضل بقى بعد كده ان احنا كنا عايزين نقلل السمبليفيكيشن بقى، عايزين نوصل للريال موديل. فده اللي انا ما لحقتش الحقيقه احضره، وده اللي هنعمله المره الجايه لما نوصل للريال موديل. وبعد كده بقى نشوف طيب الريال موديل ده بيعمل ايه في الكمبيوتيشن، والكمبيوتيشن الكلاسيكال بيعمل ايه في الريال موديل ده. يعني ليه النهارده قادرين نسيميوليت كوانتم سيستم على كلاسيكال كمبيوتر، وليه بنتوقع ان احنا في المستقبل ممكن نكون قادرين نسيميوليت كلاسيكال كمبيوتر على كوانتم سيستم. والاثنين بنتوقع تاني زي ما قلنا قبل كده ان هم يشتغلوا مع بعض، واحد فيهم مش هيكون ريبليسمنت للاخر يعني. اعتقد ان ده كان سمري مناسب بالعربي. شكرا جزيلا.
Yeah, thanks, Dr. Ahmed. So I think with this we have the summaries. So now we are going to start the Q&A session, and we'll start with Professor Isam Halim. Okay, please go ahead.
طبعا مبدئيا شكرا جزيلا على السيشن دكتور احمد، بشكرك، ودكتور طه وإليا. انا بس كان ليا استفسار، يعني اذا كان حضراتكم قلتوا اني انا لسه ما عنديش كوانتم ماشين تقدر تنفذ الكوانتم موديلز اللي احنا عاملينها، ودي حضرتك لسه قايل دكتور طه ان دي محتاجه ملايين السنين عشان تقدر تنفذ الكلام ده. هو ايه الصعوبه ان احنا نعمل كوانتم ماشين تقدر تنفذ لنا الموديلز بتاع الكوانتم موديل نفسها، اذا كان التراديشنال ديفايسز مش هتقدر تقوم بالتاسك دي؟ وانا كنت محتاج الاجابه على السؤال ده، عشان لان احنا اما نعمل موديلز كوانتم، طب وبعدين عندنا مشكله في تنفيذها، او ان احنا نعمل لها امبلمنت او ننفذها او تطلع لي سوليوشنز هتاخد بالسنين على التراديشنال ديفايس.
Yeah, a very nice question, Dr. Assam. I'm going to translate it briefly. So first, Dr. Assam is thanking the speakers, including Alain and Dr. Ahmed for their nice presentations. And he has a question about, now we have all of these hurdles about quantum computing, and the quantum hardware is not up to the level to do an actual useful computations. So why companies and scientists are bothering about making quantum models for now, despite the fact that the current available hardware is not up to the limit to meet the standards or meet the expectations of the theoretically developed models. So and also what will be the future of such things. So I'm gonna start with Alain, then with Dr. Ahmed, and then I will translate it again to to Arabic. Yeah, please, Alain. You are muted, Alain.
So very good question. I would say it's a billion euro dollar question. The future is open. It's promising, but I think the head of quantum computing, Intel, said it's a marathon. There are several hurdles, and at the moment it's really open. With the approach pursued by IBM and also Google, among others, the superconducting loop, they have made some very promising progress, especially in particular with IBM, which I'm more familiar with the interconnection of modules of a reasonable size, and now it's the time is now to play with those machines which are beyond the NISC area. We have entered the so-called utility era, at least that's what IBM claim, and for good reasons. Now I've provided, I think a key point is there is no good reason for waiting until the emergence of so-called fault-tolerant universal quantum computers. Who knows when they will be available, maybe within the next 5 years, but who knows, it might take several decades. However, the good news is there is evidence, and I provided one in my presentation, of hybrid workflows which involve high-performance computing, quantum computing, artificial intelligence, and with multidisciplinary teams with lots of work. It has already been demonstrated that there is added value with such hybrid schemes as compared to pure classical high-performance computing. And but at the same time, and this is the example I've provided from IBM and Riken, which is the Fugaku supercomputer. It appears that the initial trials, especially in chemistry, with the so-called variational quantum eigensolver, the ugly truth is it's not going to solve our problems. We need a different kind of algorithm. So this is exciting because there are low-hanging fruits. But the initial ideas, and it was the same with quantum machine learning, the initial idea of recasting successful classical approaches in the quantum computing world, it was worth trying. It gave us something to play with, especially in hackathons. It turns out this won't be fruitful. But there are other approaches which are being put forward in terms of algorithms, and so I think, to answer your question, being optimistic, pragmatic, and I would say those folks, and that includes MolKet, Taha and I, who are more on the application side, trying to deliver value and leveraging software. It's great because out of these a number of startups, eventually there will be at least one which will make a breakthrough. We don't know who yet, but yeah, it's so exciting to be more on the application side. So that's and also the other thing I would mention is that combining quantum sensing and quantum computing, there is evidence, so-called quantum learning. There is definitely a computational advantage for this combination of quantum sensing and quantum processing, quantum computing. The other open question is whether, because we know it's a bottleneck for large language models, the big data centers, the huge bottleneck is in terms of energy. It takes too much energy. Now the open question is whether with quantum computing we could achieve the same kind of computation with much lower energy consumption. It's an open research topic. and there is an association which is, I think, called the Quantum Energy Initiative, which tries to answer this question. So that's another area of exciting research. That's it from me.
Yeah, before I summarize Alain's answer, I would like to take the input from Dr. Ahmed.
Yeah, actually, the same problem exists not only for quantum computers, but also for classical computers. Even the fastest computer in the world. There are problems today that would take millions of years for El Capitan, which is the fastest computer in the world, to solve. And even if we go to the next generation of computers, the Zeta scale, which is 1,000 times faster than the current fastest computer in the world, there will be always problems that will take a million years to solve. So it is not a problem with the quantum system. It is, of course, a much bigger problem now with the quantum system because we are still in the cradle. We are still starting the field. But this problem will always exist forever. So we will have to deal with it in several ways. Sometimes we try to take subsets of the problems. Sometimes we try to simplify them. Sometimes we try, or personally in my research, I try to use intelligence, not only AI, but computational intelligence along with the high performance computing to come up with a solution. And I always give the example of you have to intelligently define your objective when you are trying to solve a problem. And I always give the example of trying to buy a rug. If you want to get a rug for your room and somebody is measuring the room using a meter, somebody else might tell you that I can measure the length of this room in angstrom or in micron. Is this a good idea? No, of course it's not, because all I need is a rug, even if it is few centimeters long or longer or few centimeters shorter, it doesn't really matter. So I have to confine or adjust my desired solution to the needed application. So all these are means of dealing with this problem, but this problem is, I think, universal and eternal. It will exist forever. Even 1 million years from now, we will have much faster computers if we still exist, and we will still have problems that would take millions of years. The need for computation is always ahead of the actual supply.
So yeah, thanks, Dr. Ahmed, for your input. So I'm gonna give a short input, and then I'm gonna summarize the answers in Arabic. So from my side, I would like to complement what Mr. Alain has said and Dr. Ahmed about this. Also, it's coming from the power of simulations. I mean, so far the hardware is not yet up to the level where you can do something commercially useful or commercially valuable with it. However, the knowledge and the skills that are generated from running those simulations or quantum simulations are really crucial for advancing many fields using the kind of knowledge. So I made a podcast about it in both languages, and one in English and one in Arabic. This is one of my hobby to do this, and then explaining that even the one in Arabic is more elaborative because of the language, and also to give more context. The kind of learning about this software, and as Alain said about the hackathons and all of this, the community building of quantum computing have increased the workforce knowledge by 10% worldwide. So the kind of simulation you learn about running an algorithm on few qubits and try to compare what you have as a perfect qubit, the result from the perfect qubit to an actual hardware. This kind of knowledge can echo in advancement of semiconductor, but also material design, even in chemistry and physics simulations. So they are really useful. So it's very nice to play also, as Alain said, to play with these machines. So we can also see the edge of physics, but also This kind of knowledge could be leveraged in a way that combining with quantum sensing, having analog chips with a quantum sensor, make quantum systems learn about other quantum systems like the annealing quantum computer. That's very useful and can open many ways to explore applications that have never been explored in a more rich way like this before. And I would like to emphasize the workforce, because it's those kind of skills really shape the mind of engineer. If you work in a high-tech company, in car manufacturing or anything, this kind of modeling skills is very helpful. Secondly, I'd like to compliment what Dr. Ahmed mentioned about the classical hardware. So it's also that problem is already there. So that's for sure. The quantum is similar to classical. The only thing is still in early development, is not up to the level where it could be reliable in actual competitions yet. So I'm gonna give now the summary in Arabic. في الأول كده كان أنا بيتكلم على حكاية الهاكاثونز، وإن الهاكاثون دي إزاي مفيدة. وحقيقة أنا هلخص طبعا الثلاث إجابات في بعض من المتحدثين الأفاضل. يعني هو فكرة انك تلعب بالسوفت وير، وانك تكون على الابلكيشن سايد او تكون على فكرة التطبيق، انك تعرف تطبق في السوفت وير ده بيدي لك حرية شديدة جدا انك تعرف تعمل كل حاجة جوه السيميليشن، جوه برنامج المحاكاة اللي عندك على الكمبيوتر. فحتى لو الهاردوير مش شغال كويس، انت ممكن تقدر تعمل كتير قوي باستخدام برامج المحاكاة دي. والحاجة التانية انك ممكن تتعلم حاجات كتيرة قوي من خلال التجارب بين مقارنة السوفت وير مع الهاردوير المتاح. وده هيفتح لك فرص كتيرة جدا انك تتعلم عن حاجات كتيرة بطريقة غنية، والطريقة الغنية دي تقدر تفيدك في تطبيقات كتيرة. وحتى في احصائيات كانت بتقول نازلة من ماكنسي وبعض الدور الاستشارات الكبيرة في بره، كانوا بيقولوا ان تم فعلا الزيادة من 10 ل 20% تقريبا في المهارات الخاصة بالمهندسين الموجودة عالميا، بسبب الجو بقى بتاع الهاكاثونز والكوميونيتيز اللي موجوده، اللي هي تعمل مسابقات بقى في البرمجه والحاجات دي كلها. وده اللي كمان هيبقى الهدف بتاع الهاكاثون بتاع اسكندريه اللي جاي، ان هو يعمل الحكايه دي. ودكتور احمد كان بيتكلم على ان مشكله الكوانتم دي، او ان المشكله بفكره ان ممكن يكون الكوانتم هاردوير عاجز ان هو يعمل حاجات دي، برضو موجوده في الكلاسيكال هاردوير، لان برضو في مشاكل كتيره السوبر كمبيوترات الموجوده في العالم ما بتقدرش تعملها. فعشان كده لازم يتم التصميم الذكي للخوارزميه اللي انت بتستخدمها، وفي نفس الوقت الطريقه اللي هتصمم بيها الكود وكده. فهو عنده تطبيقات كتيره قوي عملها واستخدم فيها الطريقه الذكيه في التصميم. اللي انا بقى طبعا بترجم صح بقى دكتور احمد، يعني الطريقه الذكيه في الايه في التطبيق للتطبيقات دي. فلو في تفاصيل اكتر طبعا هيكون متاح في السيشن العربي كده الاسبوعيه، هيكون بقى في مساحه اكتر يعني. Hey, Dr. Assam wants to ask another question. Feel free to do so.
شكرا جزيلا دكتور طه. دكتور احمد الين، بس انا برضو ما زلت عندي مشكله، مش عارف بقى حضراتكم تقدروا تفيدوني فيها ازاي. انا شايف ان حتى لما طلع الكوانتم من فتره، وبعدين لما طلع كمان الاي اي، بقى المودلز بتاعته محتاجه هاردوير سريع، ومحتاجه ان هي تتنفذ، وبتاخد مننا وقت طويل جدا عشان انفذ الحاجه اللي انا محتاجها. اذا انا اقدر اقول ان التطبيقات الثيوريتيكال ابلكيشن، سواء كانت كوانتم او اي اي، هي كده بتسبق الهاردوير بفتره، يعني هي سابقاها جامد جدا. الهاردوير ما زال عندها شورتج في الحته دي، يعني متاخره جدا. فليه انا اطلع يعني، او انا هستفاد ازاي بقى من الكوانتم او حتى من الاي اي موديل وانا ما كانش عندي الجهاز اللي يقدر ينفذ لي الحاجات دي؟ لان انت حضرتك لسه بتقول ان في بعض الانسولف بروبلم بتاخد ملايين السنين. طب ما هي هتتحل امتى لما هي لسه محتاجه تاخد ملايين السنين عشان تتحل؟ اذا هي كمان محتاجه اجهزه تنفذ الحاجات بتاع الملايين السنين دي في ثانيه او في ثواني، في دقائق. يعني محتاجه اجهزه فائقه السرعه عشان نقدر نختصر الوقت ده، والا مش هنلاقي نتائج للحاجات دي. فاخيرا انا محتاج ان احنا نعمل توصيه للناس بتوع الصناعه اللي هم المسؤولين عن الهاردوير نفسهم، ان هم يقدروا يسرعوا عمليه الابتكار في موضوع الهاردوير. ليه؟ عشان نقدر ندخل الحاجات بتاع الكيوبيت اللي بيتكلم عليها دكتور احمد، عشان نقدر نران المودلز دي ونشوف حقيقي بتطبق. لان انا حتى كمان لما اجي عندي مودلز وعايز اعمل له ران، عندي مشكله، انا مش عارف اروح فين. ده حاجه. ولو اروح في المكان، هل الحاجات دي متوفره ان انا اقدر، وهل دي فري ولا محتاجه ان انا ادفع فلوس كتير؟ فانا عندي مشكله في كده. يعني الكوانتم ده هيحل لي مشكله. طب هل الكوانتم مع حتى الاي اي كمان لما هو بيحل لي مشكله، هل المودلز دي اقدر اعمل لها ران بسهوله واطلع نتائج بسهوله في وقت قياسي، ولا اذا التطبيقات دي اصبحت غير مستفيد بيها؟ انا مش مستفيد بيها. شكرا دكتور طاهر، يعني اتمنى تكون الاستفسار وصل حضرتك.
تمام. قصدي دكتور عصام كان عندي استفسار، لو جاوبنا بالانجليزي الاجابه مفهومه عادي؟
فاهمك بفهمك.
So I would like to. So I was asking Dr. Assam if we can answer in English without going to the Arabic translation, and then he said yes. So the question, in principle, he would like to verify that as an extension for the answer that Alain and Dr. Ahmed have provided. Now the AI has the hurdle of the needs of very advanced hardware. So how and when the quantum hardware can cope with this, and is there a way to speed up the innovation in the quantum hardware? Yeah, Dr. Ahmed, please.
Yeah, actually, I just want to maybe repeat more clearly what I said. Dr. Assam is hoping that the innovators work faster to get stronger or faster machines. Trust me, they are doing their best, because this for them means trillions of dollars. So they don't need us to ask. But the problem is, you said it right. The applications are always ahead of the current hardware. And let me give you examples from other industries. At certain points of history, we wanted to move distances that we were not able to because we only had our foot and the horses. But we needed to go to far places using faster means. Of course, the use of the ships in the sea was a big thing. But again, we still wanted to go even faster to even more far places. We were not able to get any faster, so we had to take our time. So if we wanted to go to the United States from Africa or from Europe, we had to take weeks to get there, because the sea ship was the only available mean of transportation at the time. Does that mean that the people were not working on the aviation industry to get planes that are able to cross the Atlantic? No, they were working, but it is not a matter of just telling them to do it faster. They are doing their best, but sometimes you have physical limits. Like, for example, in the computer industry, about 15 years ago, we hit a technological limit. We were not able to speed up the processors anymore. It is physics. It's physical limits. We are not able to speed up the frequency of a processor. We kept able to do this since the 40s until the 2010 or something. And then we stopped. I will not get into the details of that, but we hit a physical limit. So they started working on the alternative, which is to have so many processors working together in parallel. Is this easy to do? No, of course it's not easy. It has its own problems, but it is on its way. It's getting there. So you always need more illumination in the room. People try to get more illumination, but at the same time try to use the current available illumination to do some tasks. You need to move faster to other places. So people are trying to develop means of transportation that are faster, but you still have to use what is available to you until this becomes possible. So it is not that the industry is delaying the innovation to come up with faster computers. They want to do that, but of course they are facing physical limits. And even when they solve those, as I told you, the history told us that the application will always be ahead of the available resources.
So thanks, Dr. Ahmed. So thanks, Dr. Ahmed, for your input and the clarification. Alain,
Yeah, in complement, I would say something. There is an application, of course, which is very important, is based on the Shor's algorithm, whether there will be and when we could be concerned by the emergence of a powerful enough quantum computer that it could break the RSA code, which is what he used for transactions. So it's not a symmetric protocol. And the answer is no one knows for sure, but we get prepared. Okay, but the ugly truth is the following: imagine somewhere around somewhere some team manages to make a breakthrough, hardware or software or both. Do you honestly expect this team would be allowed to share their breakthrough on archive and thing? Of course not. It would be immediately classified as secret because it's strategic, it's defense, and so maybe one day when there is such a breakthrough, it will be kept secret. And in a civil world, we won't be told until many decades after. So that's also a possibility. Hopefully there will be another application than breaking cryptography for which, for the benefit of humanity. One very where we can be hopeful is that even if there is no computational advantage in terms of capability of solving a difficult problem or doing it faster, if we can manage to lower the energy consumption, that would be awesome, because this is really the bottleneck at the moment with the AI, the generative AI, large language models. The bottleneck is, in order to create new data centers, it can only be possible if there is a nuclear plant or a powerful energy plants nearby, and there are not so many such sites around the world, and it takes 15 years or so to build a new nuclear plant to power such a data center. So this is something which is not properly. There is so much hype around what could possibly be done with the quantum computers we don't have, as opposed to being more vocal about the hope that maybe quantum computing could enable us to do computations with far less energy than classical computing. So that's my input. Thank you.
Yeah, so thanks, Alain. Thanks, Dr. Ahmed, for your inputs about the question. Hopefully now it is clear. So to summarize both, I mean, that still the quantum computing is still in early development. However, if there is a breakthrough happens, there is some expected use cases out of it, and for example in cybersecurity, but also could benefit chemistry, because chemistry also can benefit from quantum computing in general if there is a way to speed up chemistry simulations to manufacture vaccine or certain proteins for medicine and so on. So they can benefit from it. And always you can play in as a software, and as Dr. Ahmed said, there is a lot of investment in this field, because there is a lot, companies want to make money out of quantum computers. So if they find a way to make it happen, they will make it happen. The only question is if they have a breakthrough, when they are gonna announce it, and so on. So far, the good thing about the quantum computing, most of the knowledge are now open source. So you can see exactly how things are developed in IBM and so on. So, but still the progress is slow, not as was envisioned 10 years ago, that okay, maybe in the 2025 we can have this good type of qubits, but still yeah, every time the roadmap is a bit shifting. I mean, from the quality perspective, but from industry perspective, IBM has a good consistent fixed roadmap where they are really deliver what they try to promise with, and they are transparent about. However, still the quantum systems are not perfect up to the level that you can do computations with and leverage the NISC with this. However, you can combine AI with it, and then you can get more value where you use these hybrid approaches. Then you need to decide intelligently what to put on quantum and what to use from a classical hardware. So does anyone have another question? Yes, Dr. Ramadan, please go ahead.
Hello, did you hear me?
Yes.
Thank you for the lecture. I have two questions about, first question to Professor Alain. It's about the motion sensitive quantum sensor in slide number 17. So I need to know more about these sensors, because the funny thing is my research is about motion sensors and how to use them in seismology and to measure earthquakes. So I need to know more about the QNs. If you know research groups in that point, and any resources.
So I shared in the chat a link to the I think it's a press news from Lockheed Martin. To be honest with you, I'm not an expert in that field, but I found it interesting that this is the kind of application which is very much needed, because we know that the GPS works fine so long as there is no jamming or no spoofing. So I shared the link. Maybe I've got it there. Maybe I don't know whether I can see whether I can share the link, but I did share the link in the chat, and I invite you to have a look at it. And I would not be surprised that there might be other groups somewhere in the world who work on similar research technology, because it's very much needed. It's the kind of solution that some countries would like to have now rather than in a couple of years. So I invite you to check the article from Lockheed Martin, their announcement, and then maybe a query one of those large language model, ChatGPT or the French one, and hopefully you will get pointers to more information.
Yeah, Mistral, yeah, right. Yeah, the French one, the name of the French one I was giving it.
Yes, so the French one.
La, Mistral.
Oh yes, that's Mistral AI. Yes,
yeah.
And very very good.
And also open source. It's also now open source, and it's this was a good thing about it. It's open source, so similar to DeepSeek, you can check the source, and also it's now free, so you can use it. And what I heard from some connections that they used it even on Arabic, and it was giving nice results. So you even can try to use Arabic with it, and يعني يمكن تستخدم العربي مع مسترال وتشوف كده النتيجة. Then we have two questions in the chat from Tamer Asad. The first one is it expected for quantum computing to reach a deterministic computational model, or will it remain probabilistic? So I would like to hear the input from you both. I will start with Dr. Ahmed.
Well, the nature of quantum physics and the quantum mechanics is probabilistic. This is the model. Again, it relates to the topic that I was talking about. This is the model that we have until now. It is probabilistic. The interpretation of Schrödinger equation is probabilistic interpretation. So as long as you use probabilistic model to do computation, it will remain probabilistic. This is its nature. If in the future we find a way of making deterministic calculations of the quantum system, then at that time, the computation is going to be deterministic. But as long as we are using the current quantum models, the current quantum systems, they will remain probabilistic.
So thanks, Dr. Ahmed. The second question for Alain: would optical computing development present a threat to quantum computing development?
I don't know what a threat means. In this case, you mean to stop it, or you mean a competitor, or is going to compete with it? I think this is what you meant, not really to threaten it.
Yeah.
Well, of course, it can get things to. They can work together, actually. But I don't think it will threaten it in the way that it will stop it or destroy it or something. But if there is a competition, it is in a way a competition, but in another way, it's a collaboration. It's exactly like the current relationship between the classical HPC systems and the quantum. No one is threatening the other, but they are having two different tracks. They compete. And then at a certain point, they converge and they work together.
Alain?
Yes, in addition, I would say it's common sense to think that some architectures might be a better fit for some kinds of problems, especially if there is requirement to work at room temperature, as opposed to and in terms of how small it can be. But the two are definitely complementary. Think about the interconnection of quantum computers. The key players think about interconnection of quantum computers with fiber optic cables, and that there is a challenge, for example, to those IBM and Google who have superconducting loops for their qubits. They use microwave to reach the qubits, okay? And so interconnecting different modules can still be achieved with microwave, but then if they want to go beyond that, then they need to do so-called transduction to convert from the microwave to the optical wavelengths. And this is work in progress, and so you can see the synergy of the two, in other words. And you can think about especially with what I mentioned in my presentation, the availability of software, that operating system. You can think of having one quantum node that would be an IBM quantum computer with several nodes using superconducting loops, and another would be from Pascal, neutral atoms, and another one would be with IonQ, with ions, and another one from Candela with optics. So, and I think, yeah, so, but common sense should prevail, and it should be the end goal, the application that should help select the most relevant technology. That's it.
Yeah, thanks, Alain. I will add also a quick input from my side as well. So there's always I don't want to say it as a competition, so it's not really a real threat, but there is always a way to you need to define where your quantum computer and where you need to operate it. And for example, the photonic quantum chips have this ability to operate at room temperature, so you don't need this crazy cryogenic environment in order to keep them up and running and keep them away from the noise. However, it comes with the expense that your design will involve a lot of noise. This noise is not coming from the interaction with environments, but also coming from the way that the optical systems have been set up and have been defined as themselves. So there is a lot of error correction processes involved in correcting the optical chips. However, there is a lot of companies now, they believe they can scale up the photonic chips and have about 1 million qubit and so on. So those companies, they try to leverage this advantage that you can have a chip that can work in room temperature, but then there is these other hardware issues. The second optimal hardware, which we also were discussing it, Alain and I, for quite some time, is the like topological qubits. And this one, for example, I made a short video summarizing what's happening from, for example, Microsoft. There is also those one, the belief is that you can encode information in the topology of a certain material or a certain given conductor, for example, and then you can keep those information preserved. However, the problem how you can encode this information correctly on them and load them and do the control on them. So this could be a good competitor, but it's not ready yet. It's still in theory. There is no actual implementation that works in the cloud that leverages topological qubits. It's only theorized designs for the chips and so on. So yeah, that's just to highlight that how this hardware are competing with one another. Some want to say, okay, I can operate at room temperature. Some say, okay, you need cryogenics, but then you can have a good advantage because you are in a better shape to do quantum computations. Some say, okay, you can encode information with error correction built in. This is a topological qubits. Yeah, so it's a lot of there's a lot of competitions. Actually, it's not one photonic, but there is many hardware. Just to complement Alain's answer. So this question for Alain, some vendors used techniques as containers and the cloud computing. So Salim, would you mind explaining what you would like to tell? Is this a question or a comment or
a comment?
Oh, okay. Yeah. Okay. Thanks. Yeah. So
I think it's interesting because it's one topic beyond the quantum AI agent. I think I might be a good topic for presentation in the future. The idea of in terms of architecture, you see, for instance, IBM. I mean, just Qiskit V2 just came out. There are packages like Qiskit solutions, Qiskit functions, which encapsulate functionality. Okay, but in the AI arena, we have got these frameworks and these which make it easier to put together multi-agent architectures, and so there is an interesting topic, which would be to how can we make it very simple for, I would say, software architect to combine the strengths of classical computing, HPC, and quantum computing at a high level of abstraction. And I think this is already possible. It's just that there are different players and not yet talking to one another, but these approaches could be combined. So that I think, and the idea of containers is similar. By the way, NVIDIA is also a key player in quantum computing, and especially in simulation of quantum computing with a CUDA QC architecture. And NVIDIA have got a very interesting, also business-oriented viewpoint. So I think it's an exciting time. That there's some very interesting proposition put forward that are waiting for people to integrate and play with.
Yes, thanks, Alain. Does anyone have any more questions? You can also feel free to say it in English or Arabic, and we can translate. Okay, so if not, then I'm gonna just make one or two notes and also one announcement. The note that we are gonna resume the Quantum AI Lab, that held every Sunday. We have now finished 2 sessions of it. The first session was about the basics of quantum computing. The second session was a bit highlighting the tensor multiplication and how to construct a Hilbert space to represent your quantum stack, and also the quantum stack like workflow, how you map the information or encode information to qubits and then design your algorithm as a sequence of gates and perform the measurements. And the next time will be about applications. So some application like a Grover or quantum Fourier transform will be presented. I would assume that will be the next Sunday, but that's to be confirmed and will be published on the group. The second thing, we are now working on this hackathon. Hopefully, you all try to join the Open Quantum Institute course, so you get an idea and understanding about the applications and what will be done in hackathons. So hackathons also is a very good way to learn about the quantum computing and the technology in general. And we will have the International Hackathon in September, as also Youssef Eldakar has outlined in the beginning. And we will have a dry out or a trial hackathon in the summer, where we are testing the system and the students are grouping themselves in teams and so on. And there will be also experts from Egypt and from abroad, like for example, Anna will also will be invited to be part of the committee, and several others to be among the committees that will judge the presentation and give feedback, and you will learn also more skills about this for students about presentations and so on. Second announcement, we are gonna organize a small talk in Bibliotheca in the Alexandria Library when I'm present in Egypt. So hopefully, if this is when this is done, I'm gonna post a small thing about this. So we are gonna explore the hackathons, but also how to build the physics, building physics intelligence. This was a talk that has been given to a Latin to the community in Mexico. But this one will be tailored toward how to build the physics intelligence and how to build the communities and talk about the current AI models. And that will pave the way for the hackathons when I'm in Egypt, and that will be a good way to also kick off the discussions about hackathons and also construct and build the group where experts also from Egypt and abroad can work on building the assignments and the questions that could be implemented in the exercises of the hackathon. So any final words, Dr. Ahmed or Alain?
No.
Just wanted to thank you for the opportunity and for the meeting to see you all and get together. Thank you, and see you next time.
Yeah, thanks, and Dr. Ahmed, we are gonna be in contact to discuss about hackathons and everything, similarly for Alain. Yeah, so that will be so. Yeah, Bashmans Youssef, if you have any final words.
Yeah, thank you again, Dr. Taha, Alain, and Dr. Ahmed Moussa. I really learned a lot myself today. Very enjoyable presentations and lectures. And we are happy to be hosting Dr. Taha, inshallah, at Bibliotheca Alexandrina on April 17th, which will be the same day we, inshallah, also open the applications for the hackathon. So looking forward to that, and thank you very much, everyone. And thank you to our participants.
Thank you.
Yeah, thanks a lot, and the recording will be available soon.